Swayam Prabha. Digital India. Educated India.
Welcome to the Organic Chemistry paper 3. In this paper we are studying about the nitrogen containing functional groups. So in the beginning, unit 1, we are studying about nitrogen containing functional groups. In the lecture 4, we are going to study about amino compounds part 2. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. In this lecture, we will be covering the topics as given below. We are going to study about the preparation of amino compounds. Basically, in the first, in this part, we will be looking at synthesis of primary amines mainly. So there are various reactions given here. These are the common methods which can be used for the preparation of amines, and here many of the methods are specifically applicable to primary amines. We will be studying about nucleophilic substitution reactions from either alkyl halides or alcohols, how these can be converted to amino compounds we will be studying. Then we will study about the reduction reactions, mainly cyano, nitro, amides and oximes, how they can be reduced to the amino compounds we will study. Later on we will go into the another topic, which is the reductive amination reaction, where aldehydes or ketone, mainly the carbonyl compounds, how they can be converted to amino compounds we will study. Then we will study about Leuckart reaction and few rearrangement reactions also we will be studying, like Hofmann, Curtius and Lawson rearrangement reactions, and we will also study about Schmidt reaction. Then the most important synthesis for the primary amine is the Gabriel phthalimide synthesis, that also we will be studying. Then we will also study about the Ritter reaction, where tertiary alcohol can be converted to tertiary alkyl substituted primary amines we will be studying. So these are all the various topics that we will be covering in this one. So there are 4 major categories we will cover. The first one is the nucleophilic substitution reaction, then reduction reaction, then reductive amination reactions, and the rearrangement reaction. So these are all the 4 major category of reactions by which amino compounds can be prepared. So this is what we are going to study in this particular session. Welcome to the next session. In this session, we will be looking at preparation of amino compounds. There are 4 major categories of reactions to which the amino compound synthesis can be classified. The first one is a nucleophilic substitution reaction. In this reaction, we will be looking at how amines can be prepared from alkyl halides or alcohols. Then the second major class is the reduction reactions. Cyano compounds, nitro compounds, amides, oximes, etc. can be reduced to amino compounds. So we will be looking about what are the different reagents that can be used for this particular transformation. Then we will move on to the next one, which is the reductive amination. In the reductive amination, aldehydes or ketones are converted to amino compounds. And the last major category is the rearrangement reactions. In the rearrangement reactions, isocyanates are generally used as intermediates in many of these reactions. So these are all the 4 major class of reactions by which amino compounds can be prepared. We will be looking at each and every category elaborately. Let us look at how amines can be prepared. The first one is from the alkyl halides. Alkyl halides, having the general formula Rx, when treated with the cyanide, produces the cyano compound, and the cyano compound on reduction gives the amino compound. So this is one method of preparation. Then we can also prepare amines from phthalimides. The potassium salt of phthalimides, when treated with alkyl halides, give the corresponding alkylated product, which on hydrolysis leads to the formation of amino compounds. We have another method where carbonyl amide, that is carboxamide, can be reduced to the corresponding amino compounds. Here the carbonyl unit, that is the CO unit, is reduced to CH2 unit, and the amide can be prepared from acid. The X can be either OH. If it is OH, it is a carboxylic acid. It can also be a halide, that means it is an acid chloride, or it can also be an acid anhydride. So the acid halide or acid anhydride can be converted to carboxamide, and from carboxamide we can do the reduction of the carbonyl group to get the corresponding amino compound. We can also prepare amino compounds from carboxamide by rearrangement reaction. So the difference between the direct reduction of the carbonyl group and the rearrangement is 1 carbon atom. So, here we have, when we do the rearrangement, we will be losing 1 carbon atom less. That means, if the starting material has x number of carbon atoms, the product will have x minus 1 number of carbon atoms in the amino compound. So, the carboxamide will have 1 additional carbon atom that is actually lost as a CO2 unit. So, that is how the rearrangement leads to the final amino product. There is a isocyanate which is involved as a intermediate in this reaction. When we study about this reaction, we will look at how the reaction actually proceeds. Then the next one is the reduction reaction. So, we have seen two types of major reactions. Actually, one is the nucleophilic substitution reaction, another one is a reduction reaction. In the reduction reaction, we also have the reduction of nitro groups can lead to the corresponding amino compounds. The next one is nucleophilic substitution reaction and the reductive amination reaction. So, if it is a carbonyl compound, that is called the reductive amination reaction. If it is an alkyl halide or alcohol, it is a nucleophilic substitution reaction. In both the cases, we actually treat the compound or the starting material with ammonia, and ammonia undergoes reaction with these substrates to give the corresponding primary amines. We can also convert isocyanate to the corresponding amino compounds. So, here basically we do a hydrolysis of this isocyanate, which leads to the formation of amino compound. The isocyanate can be prepared from acyl acid, or we can also convert the acyl acid directly to the amino compounds. We can also convert an acyl acid to the corresponding isocyanate. From the isocyanate, we can also prepare the amino compound. So, these are all the various methods by which a primary amine can be prepared. We will be looking at each and every reactions elaborately. So, let us look at the various reactions what we will be looking in this particular session. The first is the nucleophilic substitution reaction, that is nucleophilic substitution of alkyl halides or alcohols. Then the next major category is the reduction reaction. We will look at cyano group or the nitro group or the amide, carboxamide or the oximes, how they can be reduced to the corresponding amino compounds we will be looking at. The reductive amination reaction, in which an aldehyde or a ketone, that is a carbonyl compound, can be converted to the amino compound. We will see what are the different reagents that are used in this reaction. And then we will also be studying about various reactions like Leuckart reaction. The hydrolysis of the isocyanate is another major class of category which we will be looking at. Basically, Hofmann rearrangement, Curtius rearrangement, Lawson rearrangement and Schmidt reaction are the various reactions which all involve this particular isocyanate as the intermediate, and we will see how each rearrangement is getting converted to the corresponding isocyanate, and how the hydrolysis of the cyanate leads to the hydrolysis of the isocyanate leads to the final amino compound we will be looking at. There are also other methods like Gabriel phthalimide synthesis, which is a very important reaction for the synthesis of primary amines. We can also prepare amino compounds from amino acids or Grignard reagents, or also finally we will look at the Ritter reaction. So, this is a very crucial reaction. Here basically tertiary alcohols are converted to the tertiary alkyl substituted primary amines. So, this is a very important reaction. So, we will be looking at all these reactions. So, let us start with the first reaction, which is the alkyl halide from alkyl halide. So, this method is called as a Hofmann method. The Hofmann method is nothing but the ammonolysis of an alkyl halide by either ammonia in a sealed tube at high temperature, that is ethanol is used as a solvent, and at 100 degrees centigrade we carry out this reaction. This reaction is run in a sealed tube. The reason is, when we are using ammonia, ammonia is a gas. So, this will escape in a normal reaction flask. So, to avoid that, the reaction is carried out in a sealed tube, so that the ammonia gas remains within the reaction medium. And primary, secondary and tertiary amines are obtained by this method. Even quaternary ammonium salt is also formed in this particular reaction. So, here is a complete detail of reaction mechanism for each step. Then alkyl halide is treated with the amine, ammonia basically. This is our amino derivative. and when amine is reacted with the primary alkyl halide, we end up with the primary amine as shown here. So, in this particular reaction, the halogen from the alkyl halide and one of the hydrogen combine together to form the corresponding halo acid. So, that is the halo acid that is formed here. So, amine is basically a basic unit, amine is basic in nature, and this HX is acidic in nature. So, there is a acid base reaction which occur to give a complex of this nature, that is basically the hydrochloride salt or the hydrohalide salt of the primary amine is formed. So, this is how we end up with the formation of the primary amine. But the primary amine in the reaction medium, we have the basic ammonia. So, this ammonia can now react with the acid part, acid halide part. So, these two combine together to form the ammonium salt. So, the ammonium salt is formed as a byproduct which releases the primary amine. Once the primary amine is liberated as a free unit, this primary amine can further react with one additional equivalent of the alkyl halide to give the secondary amine. So, this secondary amine can further react with one more equivalent of the alkyl halide to give the tertiary amine, and finally, this tertiary amine reacts with one additional unit of the alkyl halide to give the quaternary ammonium salt. So, in this reaction what happens is, even though we want to prepare the primary amine, this reaction is never stops at the primary amine stage. This reaction actually continues because we are running the reaction at a high temperature and also in a sealed tube. So, that means there are more ammonia, primary amine and the other amino derivatives are formed or present in the reaction, and each of them can react with the alkyl halide, and this reaction being a nucleophilic substitution reaction, this goes on till we get the quaternary ammonium salt. So, although this method is a very old method used by Hofmann for the preparation of primary amines, this reaction is seldom used currently. The reason is the reaction always leads to mixture of products like the required primary amine, some amount of secondary amine is also formed, tertiary amine is also formed, and even the quaternary ammonium salt is formed. So, if at all we have to use the same reaction like use of only ammonia for the preparation of primary amine, then what is required is we need to use excess of ammonia. So, when we use excess of ammonia and less amount of the alkyl halide, so what happens is, in this particular case we have plenty of the ammonia molecule present in this reaction and there is less amount of the alkyl halide present. So, they react together to give only the mono substituted product, that is the RNH2 is formed, and this RNH2 will not further react with the alkyl halide because the alkyl halide is present in less quantity. So, that means we can actually selectively prepare primary amine if we use large excess of ammonia in this particular preparation. But if at all we need to prepare a tertiary amine from this method, then what we need to use is we actually need to use 3 equivalent of the alkyl halide, because for every alkyl group, one alkyl group can replace one hydrogen from the ammonia molecule. So, ammonia has 3 hydrogen atoms. So, each hydrogen can be replaced by one alkyl group. So, if we are using 3 equivalent of the alkyl group, then we end up with a tertiary amine. So, this is how we can prepare tertiary amine by this method if we use 3 equivalent of the alkyl halide. And if you look at the reactivity of the halogens, the iodines react much faster or much better compared to the bromo derivatives, followed by chloro derivatives. Generally, if we have to prepare a primary amine from an alkyl halide, it is better to use the alkyl iodide. So, the alkyl iodide gives the amine very effectively, whereas conversion of RCl to RNH2 is very slow. So, this reaction is a very sluggish reaction. So, that is the reason people prefer to use alkyl iodide for the preparation of amines from primary alkyl derivatives. Instead of ethanol and ammonia solution what we have seen earlier in the Hofmann method, if we use liquid ammonia, then we can actually get better yield of this particular product, that is the primary amine. But again, this is not an exclusively will give the primary amine as the final product. Let us say we know the iodides are much better reactive compared to the chloride. So, if we start with ethyl iodide and treat it with ammonia, that is the liquid ammonia, our primary amine, that is the ethylamine, is formed in around 46% of the product is formed. But this reaction does not stop here. The reaction also continues to give the secondary amine in 31% yield and also the tertiary amine with 17% yield. In other words, if you look at the product ratio, 50% of the primary amine is formed along with the combination of secondary and the tertiary amine in 50% yield. So, that means this reaction is not a very selective method for the preparation of primary alkyl amines. Of course, when we talk about the secondary amine, this reaction actually works better for the primary amines, and if we are using the secondary alkyl halide, especially the isopropyl is the only unit that gives the required product. All other cases, that means if you have any other alkyl halide, secondary alkyl halide or the tertiary alkyl halide, what happens is elimination is a major side reaction, because we know ammonia is a base. So, when ammonia is a base, in this particular case, elimination reaction also is possible. So, that is the reason if we are using ammonia for the preparation of secondary or tertiary alkyl amines from alkyl halides, we always end up with the elimination product also. So, that is the reason this reaction or this method is seldom used for the preparation of secondary or tertiary amines. So, there are also other methods. We have seen about the alkyl halides substitution reaction. Now, let us look at the substitution reaction of alcohols. So, the ammonolysis of alcohols, that means reacting an alcohol with ammonia produces primary amine with water. So, since water is formed as a byproduct, either using alumina or copper chromate or other reagents which can remove the water, facilitate this particular reaction. So, similar to alkyl halides, if we use large amount of the alcohol, then obviously we are going to end up with the secondary amine as well as the tertiary amine are also formed in that reaction. So, similar to the previous case like alkyl halides, if a large excess of the ammonia is used, then we can selectively prepare the primary amines. So, to prepare primary amine exclusively or in larger quantities, we need to use large excess of ammonia. So, this is another method. That means we have seen two substitution methods. One is from alkyl halides, ammonolysis of alkyl halides gives the primary amines. Similarly, ammonolysis of alcohols also give the primary amines. So, these are all the two major methods. Then we will move on to the next reaction, which is the reduction reaction. So, we have seen the first category substitution. Now, we are going with the reduction reaction. So, metal catalyzed reductions in the presence of acid basically gives the amines. So, the metal catalyzed reduction of the nitro groups when we are using the nitroalkane with hydrogens in the presence of a metal catalyst, either iron HCl or ranane nickel can be used for this particular reaction. We end up with the reduction of the nitro group. The NO2 group is getting converted to amino group with the concomitant formation of water molecule. So, this is a very good method for the preparation of higher molecular weight amines, because higher molecular weight nitriles are easily prepared from the corresponding carboxylic acid. So, after nitro compound, we have the cyano compound reduction. So, the cyano compound on reduction gives the corresponding amino compounds. So, here we have one carbon. So, that is the reason we have a CH2 unit here between R, the alkyl group, and the nitrogen unit. So, if you look at the structure here, we have an alkyl group and we have a nitrogen. So, between alkyl group and the nitrogen we have a carbon. So, this carbon is also reduced to the CH2 carbon. So, that is the reason we have one carbon which is actually from the starting material cyanide carbon. So, this reduction is most preferred reduction, because in this particular case the cyanide can be formed from the corresponding carboxylic acid. So, the carboxylic acid can be converted to cyanide. So, when we have this higher molecular weight nitriles, so this higher molecular weight nitriles can be easily reduced to the corresponding amino compound. So, this method is generally used for the preparation of higher molecular weight primary alkyl amines. Let us look at other reduction methods. So, here we are going to look at two different methods. One is the reduction of oximes. The reduction of oximes using sodium in ethanol generally produces the primary amines. We have branching on this particular carbon. So, depending on the branching, we end up with the corresponding branched final product. So, if we have a hydrogen atom here, then we end up with the 2 hydrogen atoms here in the final product. If we have one alkyl group, that means if we have a di substitution on this particular carbon, our final product is also having the di substitution as shown here in this final product. So, whatever is the substitution is retained in the final product also. So, this is how the reduction of oximes takes place. This hydroxy unit is lost and we end up with the corresponding amino derivative. The hydroxy unit is lost as a water molecule. Let us look at the next reduction, which is the carboxamide reduction. That means the reduction of the carbamides in the presence of sodium and ethanol gives the corresponding amino derivatives. Of course, we also have the Wolff-Fishner reduction and the Clemmensen reduction, which also reduces the carbonyl group. And here we are looking at the sodium ethanol reduction, and in this case we also get some amount of the secondary amine as the byproduct if we use sodium and ethanol. But if we use ranitidine as the catalyst, in that case we generally or exclusively get the corresponding primary amine as the major product. Similarly, lithium aluminum hydride can also be used to reduce various compounds like the nitro group or the amide carboxamide or the cyanide or the oximes can be reduced to the corresponding amino compounds using lithium aluminum hydride. So, this is basically the hydride reduction, that means H minus unit is added in this particular case. Whereas in the case of sodium and ethanol, we generally have a radical mechanism, that means H dot is added in those cases, and in ranitidine basically it is the hydrogen atom is added. So, depending on what is the reagent that is being used, the mechanism for this particular transformation can change. Let us move on to the next category. This is the third category we were looking at, that is the reductive amination reaction. So, we have seen nucleophilic substitution reaction, we have also seen the reduction. Now, the third category, which is the reductive amination reaction or reductive alkylation reaction. So, in this reaction a carbonyl compound, basically here we have taken a ketone as an example. The ketone reacts with the amine. Here this is the ammonia is the amine derivative. We can also use for the preparation of primary amine, we generally use ammonia as the reagent. So, ammonia when reacted with the carbonyl unit, that is ketone, in the presence of a ranitidine and hydrogen reducing conditions, gives the corresponding amino compounds. So, this reaction actually proceeds via an imine formation followed by the reduction of the imine to the corresponding amino compound. The same reaction can also be carried out in the presence of ammonium chloride and Adams catalyst. So, either of the conditions can be used for the preparation of ammonia compounds from the carbonyl unit. So, this reaction, as I mentioned, this is a reductive amination reaction. That means an amine unit is added and a reduction takes place. So, this is a reduction, this is the addition of the amino unit. So, that is the reason this reaction is called reductive amination reaction. So, here we can also say the other way, we are using an alkyl unit, we are reacting with an amine. So, reduction and the alkyl unit both are happening together. So, we can also call this as a reductive alkylation reaction. So, these are all the two ways the reaction can be represented. And in this particular case, we end up with a very small amount of the secondary and the tertiary amines. These are formed as a byproducts. Otherwise, this reaction generally gives a primary amine as the major product. And here the reaction is carried out under pressure, that means 20 to 150 atmospheric pressure. That under high pressure the reaction is carried out. The reaction temperature may be from 40 to 150 degrees centigrade. So, that means this reaction is also generally carried out in a sealed tube. The next one is a Leuckart reaction. So, here we are converting a carbonyl unit, that means aldehyde or ketone, to amines by the reductive amination reaction. And here what we do is, we basically, instead of a ammonia unit, ammonia, we are actually using a ammonium salt, that is ammonium formate is generally used, or formamide is also used. Instead of using ammonia directly in this reaction, the ammonia is formed in situ in that particular reaction, because this particular ammonium formate on heating produces the ammonia unit, and this is how the reaction actually proceeds. The carbonyl unit adds the formamide unit is added to the corresponding carbonyl compound, and here basically the nitrogen is being donated by the ammonium formate or the formamide, and this also acts as a reducing agent. And here again the reaction is carried out at a high temperature like 120 to 160 degrees centigrade. And when we are using ammonium formate, that gives a much better yield of the primary amine compared to formamide when it is used as a reagent. So, this is the ammonium formate. The ammonium formate reacts with the carbonyl compound to give this particular formamide derivative, and this formamide derivative on acid based hydrolysis leads to the corresponding primary amino compound as the final product. And in this particular reaction, carbon dioxide is produced as a gas, and ammonia is actually produced in this particular reaction, that is the decomposition of ammonium formate leads to the ammonia, which adds to the carbonyl compound, and then we end up with this particular intermediate. Let us look at preparation of primary amines by hydrolysis reaction. So, here we will be looking at isocyanate as the major starting material for the preparation. So, the hydrolysis of the isocyanate, especially in the presence of an alkali, gives the primary amines. Of course, isocyanates are not commercially available. So, that is the reason this method is not generally used for the preparation of primary amines. But if the isocyanate can be formed as an intermediate in a reaction, then that is the most preferred one for the formation of primary amines. Basically, hydrolysis of isocyanate is a two-step process. So, in the first step, what happens is, we are getting a unstable carbamic acid, and this unstable carbamic acid. So, this is the carbamic acid. So, this is having the CO2 unit. So, when this CO2 unit is lost, then we end up with the corresponding amino compound. So, we have the R, H, N and H, then there is one hydrogen here. If these two combine together, we end up with the primary amine as shown here. And if we are using a basic condition, that means KOH is used, this KOH can trap the CO2 molecule to form the potassium carbonate. So, that is how the reaction actually proceeds to give the primary amines. So, isocyanates on hydrolysis gives a unstable carbamic acid which loses carbon dioxide molecule to give the primary amine. And if you are using less amount of water, so this reaction is a very crucial reaction in which we have to use adequate quantities of water molecule. If adequate quantities of water molecule is not used, then what will happen is, there will be some unreacted isocyanate. If an unreacted isocyanate is present in the reaction medium, we have the primary amine. So, the unreacted isocyanate and the primary amine react together to give a urea derivative as shown here. So, this is the byproduct in this reaction. So, that is the reason to avoid the byproduct formation, we do need to use excess of water in this particular hydrolysis reaction. So, if you use excess of water, then we can completely avoid the formation of this byproduct, then we end up only with our required primary amine as a major product. Let us look at isocyanate as intermediate. So, we have seen that preparation of isocyanate is very difficult, and they are not generally used as a starting materials in many of the reaction. So, if the isocyanate is formed as an intermediate, then it is possible to prepare primary amines from hydrolysis of the isocyanate. So, we are going to look at what are the different rearrangement reactions in which isocyanate is formed as an intermediate. The first one is the Hofmann rearrangement. Here a primary carboxamide is treated with bromine and sodium hydroxide. The next one is the Curtius rearrangement. Here what we do is the thermal decomposition of the acyl acide or acid acide leads to the formation of isocyanate intermediate. And the next one is the Lawson rearrangement. Here hydroxamate ester and a base is treated together to form the isocyanate. And then we have the Schmidt reaction. So, here acid is converted to acid acide, and this acid acide is decomposed thermally to form the isocyanate. So, these are all the various reactions in which isocyanate was involved as an intermediate. Let us look at each reactions individually. The first one is the Hofmann rearrangement. So, in this case we have a primary carboxamide. So, the primary carboxamide is treated with bromine and sodium hydroxide. So, when we treat these two things together, we end up with the intermediate, that is the isocyanate is formed in this reaction, and this isocyanate on hydrolysis by losing carbon dioxide molecule produces the primary amine. So, here if you look at the overall reaction, this reaction actually involves the oxidation of the nitrogen atom. So, that means this particular nitrogen is oxidized, followed by rearrangement of the carbonyl and the nitrogen to give the isocyanate intermediate. So, here what happens is, if you look at the connection, actually here we have the R, then we have a carbon atom and the carbonyl carbon and the nitrogen. So, that means the nitrogen is attached to the carbonyl carbon, but if you look at the intermediate, the alkyl group is actually attached to the nitrogen. That means there is a shift of this alkyl group to this particular nitrogen atom happens. So, that is why we call this as a rearrangement reaction. So, this leads to the formation of the, now what happens is this particular bond breaks, and then nitrogen carbon oxygen bond remains as intact. So, the nitrogen carbon oxygen bond remains as intact, only the alkyl group is shifted or migrated from the carbonyl carbon to the nitrogen oxygen. This is basically the electron deficient nitrogen. So, that is how this rearrangement actually takes place. This electron deficient nitrogen takes this particular alkyl group with its bonded electron pair, and then we end up with the isocyanate intermediate, and hydrolysis of this isocyanate intermediate leads to the final product, that is the primary amine. The next one is the Curtius rearrangement. So, in the Curtius rearrangement we have a acyl acide. So, this is the N3 unit. So, this acyl acide on thermal, that means heating, leads to the formation of this particular intermediate, that is the isocyanate. So, here again this is also a similar rearrangement reaction in which the alkyl group migrates from the carbonyl carbon to the electron deficient nitrogen atom. So, this leads to the formation of the isocyanate, and this isocyanate as usual undergoes hydrolysis by the loss of carbon dioxide molecule to give the amino compounds. So, the driving force for this reaction is the formation of CO2 gas. Since it is a gaseous molecule, this actually escapes from the reaction mixture and makes the reaction move in the forward direction. And the next one is the Lawson rearrangement. So, in this Lawson rearrangement we have the hydroxamate ester. This is treated with a base. and when we treat a hydroxamate ester with a base, it is converted to the isocyanate intermediate. This also follows the very similar rearrangement to the Curtius and the Hofmann rearrangement, and we end up with the isocyanate as the intermediate. And once the isocyanate is formed, then what happens is this is hydrolyzed to the corresponding primary amine. Next is a Schmidt reaction. So, in this Schmidt reaction, we are actually making the intermediate from the Curtius rearrangement, that is the acyl acid is formed. So, how do we prepare the acyl acid? We treat the carboxylic acid and the hydrozoic acid. So, the treatment of carboxylic acid and hydrozoic acid leads to the formation of the alkyl acid, and acyl acid leads to the formation of the acyl acid, and this acyl acid on heating rearranges to give the isocyanate, and the isocyanate on hydrolysis leads to the final primary amino derivative. So, this reaction is basically carried out in the presence of acidic condition. So, we can use a Bronsted or a Lewis acid, and here again the loss of nitrogen also is, here we have two nitrogen atoms. So, these two nitrogen atoms are lost as the nitrogen gas. So, that is where what we have written here is the loss of nitrogen is from the acid unit, and this is the driving force for the reaction to move forward. And when we react an acid with the carboxylic acid, we end up with the acyl acid. So, this is very similar to the, once we have the acyl acid, the reaction then proceeds via the Curtius rearrangement. So, the formation of the isocyanate by the loss of nitrogen, then finally we hydrolyze this isocyanate to the corresponding primary amine derivative. So, all these rearrangement reactions involve isocyanate as the crucial intermediate. So, the preparation of the acyl acid can be carried out using either hydrozoic acid, or we can also use alkyl acids. Instead of HR3, we can also use RN3. So, this is the alkyl acid. So, the alkyl acid can also react with the corresponding carboxylic acid to give the acyl acids. This reaction can be carried out in the presence of Lewis or Bronsted acids. Let us look at another important class of reaction, that is the Gabriel synthesis or a Gabriel phthalimide synthesis. So, here the conversion of the primary alkyl halide to the primary amine is done. So, here we are using basically the phthalimide, because this is the compound which is shown here is the phthalimide. So, this reagent is the most crucial one which is used in the synthesis of Gabriel phthalimide synthesis. So, what is the difference between our normal SN2 reactions where we use alkyl halide to the formation, because alkyl halide can be converted to primary amine. So, this is the one we have seen earlier. So, this is nothing but the SN2 substitution. So, this reaction always leads to the formation of primary, secondary and tertiary alkyl amino derivatives, whereas if you use the Gabriel synthesis, this reaction exclusively gives the primary amines only. So, this reaction does not produce secondary or tertiary amines, as we have seen in the previous case of alkyl halides and ammonia reaction. So, that is the reason this reaction is highly important for the synthesis of primary amines. So, in this method, the phthalimide is treated with an alkali base to form the corresponding salt. We will look at let us look at the various steps involved in this reaction. The first one is the conversion of the phthalimide to the corresponding salt. Then the N-alkylated, this corresponding salt is N-alkylated with primary alkyl halide to give the N-alkyl phthalimide. Then what happens, the N-alkyl phthalimide is hydrolyzed. So, there are the three steps happening in this particular reaction, and let us look at what are the three steps which we are talking about. So, this is the first one, which is the phthalimide. So, we start with the phthalimide, and this phthalimide is treated with the potassium hydroxide. That means a base is treated with this one. This hydrogen is a acidic hydrogen, because this hydrogen is attached to electron withdrawing carbonyl groups. So, that is the reason this is a highly acidic hydrogen, and this highly acidic hydrogen can be replaced by the potassium base, that means potassium hydroxide can replace this hydrogen. So, we end up with the potassium salt, and once we form the potassium salt, this potassium salt can react or can be alkylated with the alkyl halide. So, here we prefer to use alkyl iodide, because we have seen earlier also the reactivity of alkyl iodides are far better compared to alkyl bromides, which is much better than alkyl chloride. So, that is the reason here we are using alkyl iodide as the reagent. So, this alkyl iodide can replace the nucleophilic attack of this imide salt happens on the alkyl halide with concomitant removal of the iodide leads to the formation of this alkyl intermediate, alkyl phthalimide intermediate. This can be hydrolyzed using water or acidic conditions. We can use it to hydrolyze this one. We end up with the phthalic acid as one of the byproduct, and the primary amine is formed. In certain cases, if the alkyl phthalimide is not easily hydrolyzed by the treatment with water, we can also use hydrazine. Hydrazine can also be used to cleave this particular RN bond. So, this particular bond is cleaved, we end up with the corresponding amino derivatives. So, hydrazine can be used for this particular reaction. This reaction is very selective for the primary alkyl halide conversion to the corresponding primary alkyl amine. So, the primary alkyl amine can be easily prepared from primary alkyl halide using this particular procedure. And when we use secondary alkyl halide, this reaction does not proceed. So, that is the reason we can very selectively use this Gabriel phthalimide synthesis for the preparation of primary amines. So, let us look at some of the important features of this particular reaction. So, as we have mentioned, the amide hydrogen is acidic in nature, that means the pKa of that particular hydrogen is 9. So, it can easily be replaced by the base to produce the anion. So, this is the most crucial step. So, that means in this particular case we have this NH, we have a 2 electron withdrawing group, that is a carbonyl unit attached to this particular nitrogen. So, this hydrogen is highly acidic in nature. So, this can be easily replaced by the potassium salt. So, when we treat with the base, so what happens is this acid base reaction takes place and the potassium is now attached to the nitrogen atom. So, this is the acid base reaction. So, the salt is formed. So, here the potassium phthalimide is the salt that is formed, and this phthalimide anion is actually a very strong nucleophile. So, this remains as N minus and K plus. So, that means the negative charge on nitrogen is basically the phthalimide anion. So, this is a very strong nucleophile, and this anion can now replace the suitably positioned halide. So, we have the alkyl iodide, Ri is here. So, we have a nucleophilic nitrogen. So, this nucleophilic nitrogen can attack this alkyl group and then the iodide is lost. So, this is the SN2 reaction. So, we end up with the nucleophile attaching to the alkyl unit. So, these two are joined together. So, in other words, we end up with the N-alkyl phthalimide, and hydrolysis of this particular product leads to the primary amine. So, this is the most important thing in the case of phthalimide reaction. Let us look at the other preparation of amines, primary amines. So, from amino acids we can prepare primary amines. The amino acids can be decarboxylated, because what we have is only the carboxylic acid unit. So, if the carboxylic acid unit is knocked off or it is removed, then we end up with the corresponding amino compounds. So, we have a CH2, RCH2, NH2 will be there. So, how the decarboxylation can be carried out is basically by the caustic baryta. When we treat the amino acids with the caustic baryta, the CO2 is lost and we end up with the RCH2, NH2 as our primary amine. We can also prepare amino compounds from Grignard reagent. So, when a Grignard reagent is treated with the chloramine, So, this chloramine, here we have the halogen, we have the magnesium and the halogen is there from the Grignard reagent. So, these two combine together to form the MgXCl, and whatever is left out is we have the R group, we have the NH2 unit. So, R and NH2 unit form to give the primary amine. Of course, this is a very simplistic way of representing the reaction, but the reaction mechanism is quite different. But for your easy understanding, I have just marked like a circle and I just connected R and NH2. So, this is a easy way of understanding how the reaction actually proceeds. The next one is the Ritter reaction. So, this is a very important reaction for preparing tertiary alkyl group amine compounds, because here we have the tertiary alcohol. This is a tertiary alcohol. So, this tertiary alcohol is treated with sulfuric acid to give the corresponding sulfate ester, and this sulfate ester can be treated with either HCN or RCN. We can also use alkyl cyanides, or we can use hydrogen cyanide also. So, when these two react together, that is the sulfate ester and the cyano derivative react together, we end up with this particular intermediate, and this intermediate on losing water produces the corresponding alkyl N-alkyl formamide. So, this is the alkyl unit. So, this is the alkyl unit and this is the formamide unit. So, the alkyl unit is attached to the nitrogen. So, this is called the N-alkyl formamide unit, and this N-alkyl formamide unit on hydrolysis gives the corresponding amino compound. So, this is the primary amine having a tertiary alkyl group. So, this is the best method for preparing primary amines having tertiary alkyl groups. The earlier methods whatever we have seen, because the Gabriel phthalimide synthesis cannot be used for the preparation of this tertiary alkyl unit, because that is mainly used for the primary alkyl compounds only, because the SN2 reaction of the primary alkyl halides happens much better than the tertiary alkyl halides. So, the preparation of tertiary alkyl substituted primary amines cannot be prepared by Gabriel phthalimide synthesis. So, in those kind of cases, Ritter reaction comes as a rescue. That means we can use Ritter reaction to prepare a primary amine containing a tertiary alkyl unit. So, let us recap what we have seen so far about the primary amine formation. So, the first one what we have seen is the nitro to amine reduction. So, here one of the limitation with the nitro to amine reduction is other functionalities like alkenes and other things are also reduced. So, we have to be very careful. The substrate should not have other reducing functionalities. If other reducing functionalities are present in the nitro compound, then reduction of nitro to amine is not easily carried out using Raney nickel or iron and HCl combinations. The Raney nickel hydrogen is generally used as a industrial preparation of nitro reduction. So, this is used in large scale preparations, whereas tin and HCl is used for the laboratory preparation. So, there are two major ways by which the reduction can be carried out. If an industrial process is required for the nitro to amino reduction, people prefer the Raney nickel hydrogen route. And if an industrial in the laboratory scale for a very small scale preparation, if you are going to use, then the tin HCl method is the best method for the small scale preparation in the laboratory. The next one is the alkyl halide to amine using ammonia. So, this is the initial SN2 reaction what we have seen. So, in this reaction we actually end up with a mixture of product. That means along with the primary amine we also end up with the secondary amine, tertiary amine, and even quaternary ammonium salt is formed. So, this is not generally used for the preparation of primary amines exclusively, and also this reaction involves elimination as a major side reaction. So, that means if you are going to prepare a secondary or tertiary substituted compounds, then this reaction is not a important reaction or a useful reaction for the preparation. We can also prepare amines from the alkyl halides using cyanides. So, in this particular case, when we use a cyanide, we are actually using a carbon nucleophile. So, that means we are actually adding one more carbon to the starting alkyl halide. If the alkyl halide has R number of carbon atoms, the final product will have RCH2NH2 is going to be our final product. That means we will have R plus 1 carbon attached will be the final product. So, that is the addition of one carbon unit can be carried out using the cyanide reaction. Then we also have seen about the carbonyl to amine conversion. So, we have seen a couple of reactions. One is the formation of the amine followed by reduction. So, this is nothing but the reductive amination reaction we have seen. So, here the substitution on the nitrogen increases by one alkyl group. So, if we use ammonia, we end up with a primary amine. If we start with the primary amine, then we get a secondary amine after the reaction. So, if we start with the secondary amine, we end up with a tertiary amine. So, that means one alkyl group adds to the nitrogen atom at a time in this particular reductive amination reaction. Of course, this is a very good method for the preparation of secondary alkyl group, because secondary alkyl group do not undergo elimination in this particular case. So, we can actually use a secondary alkyl carbonyl group. Say for example, if we have to prepare a cyclohexanone to the cyclohexyl amine if we want to prepare. So, this is a very good method. So, when we treat the cyclohexyl amine with the ammonia, then we can end up with the formation of this particular amine very easily. And if we use ammonia, sometimes along with the primary amine, we also end up with a secondary amine as a minor byproduct. So, these are some of the characteristics of carbonyl to amine reduction. And we also have amide to amine reduction reaction. So, we have two types of reaction. One is the carboxamide reduction giving to primary amine directly with the same number of carbon atoms. So, here we use reducing agents like Raney nickel and hydrogen, or Wolff-Kishner reduction, or Clemmensen reduction, or similar reductions can be used. And if you use the Hofmann rearrangement condition, that is sodium hydroxide and bromine, in that case we also end up with the primary amine, but we will have one less carbon atom from the starting carboxamide. So, that is the difference between Hofmann rearrangement and the normal reduction of amides. Then finally, we have also seen about the reduction using lithium aluminium hydrates. The lithium aluminium hydrate can reduce nitro compounds, amides, oximes, cyanides, etc. to the corresponding primary amines. But if we use the aromatic nitro compounds for the same reduction of preparing aromatic amino compounds, the reduction stops only at the azo derivatives and we do not get amine. So, this is one of the limitations you have to remember. The LAH reduction of alkyl amines or NO2, when R is a alkyl group, can be reduced very effectively to the corresponding amino derivative. But if the R is a aryl unit, that means if we have the aromatic system, then the reduction of this nitro group to the corresponding amino derivative does not take place using lithium aluminium hydrate, because in this case what we end up is we will end up with the azo derivative. So, we have a double bond nitrogen and then we again have the aromatic unit here we have. So, those kind of product will be formed. So, that is the reason aromatic nitro compound cannot be reduced using lithium aluminium hydrate to get the corresponding amines. Let us recap the summary what we have studied so far. We have studied four major class of reactions for the synthesis of primary amines. Of course, many of these reactions can also be, some of the reactions can also be applied for secondary and tertiary amines. So, the major reactions what we have covered is mainly for the synthesis of primary amines. The first one is the nucleophilic substitution reaction. So, in this reaction we have studied how alkyl halides or alcohols when reacted with ammonia can be converted to primary amines. We have seen. We also studied about the reduction of various functional groups like cyano, nitro, carboxamides or oximes, how they can be converted into the amino compounds we have seen, and what are the different reagents that are used and what are the different conditions that are employed we have seen. Later on we studied about the reductive amination reaction. So here we carry out two types of reactions. One is introduction of the amine group, the second one is reduction of the double bond, that is the carbonyl group. So these are all the two things combinedly called as the reductive amination reaction we have studied. That means aldehydes or ketones, mainly the carbonyl compounds, how they can be converted to the amino compounds we have seen. And the next major category what we have seen was the rearrangement reactions. Here we studied about the Hofmann, Curtius and Lawson rearrangements. So how the isocyanate can be converted to the amino compounds we have seen, and how the starting material, say for example carboxamide can be converted to isocyanate, or acylazide can be converted to isocyanate. That those are all the reactions we have seen. That crucial intermediate in this kind of rearrangement reaction was the isocyanate. So how the isocyanate on hydrolysis can be converted to amino compounds we have seen. And in the rearrangement reaction, what is the shift or the rearrangement of the alkyl group, how it takes place, that also we have seen. And we have also studied about the Schmidt reactions. And another important reaction what we have studied was the Gabriel reaction or the Gabriel phthalimide synthesis. So in the nucleophilic substitution reaction, we have seen that primary alkyl halides can never stop the reaction with the primary amines formation, because the reaction continues till we get the quaternary ammonium salt. So that is a major side reaction in the case of normal nucleophilic substitution reactions. How the Gabriel phthalimide reaction can be selectively used for the preparation of primary amines we have seen. We have also studied about how the tertiary alcohol can be converted to the tertiary alkyl substituted primary amines under Ritter reaction conditions. With that, we conclude this session on the synthesis of primary amino compounds. Thank you.